Hello students, let us start our new chapter, chapter number 9, Mechanical Properties of Solids. Let us go through its introductory part. As we know that the motion of a body depends on how its molecules, atoms and mass is distributed all over through the body. These solid bodies can be stretched, compressed, can be bent. It cannot be perfectly rigid. Generally, in our sense that solid body would be there, then it must be a rigid body. But it is not so, as compressible and stretched body also will be available. If any solid body is there and if we want to change its shape and size, then by applying a proper force in a particular direction, we can change its shape. So we cannot say that it's a perfectly rigid body while we can change its dimension. So here the body which tends to regain its original shape and size after applying a force, and that force will be removed. Initially, while the force is provided, its shape and size can be changed. But while we remove that particular applied force, then that particular body will regain its original shape and size, which is known as elasticity. This property is known as elasticity, which allow to deform the that particular body itself, and that deformation is known as elastic deformation. If we apply a force on a lump or mud, so what will happen? They have no tendency to regain its shape, so that would be permanently deformed condition will be available, which is known as plasticity. The property is known as plasticity, and that substance is known as plastic. So here, while we apply the force on a body, so the body will develop the restoring force. This restoring force generated within a body that is in equal magnitude and in opposite direction of the applied force. This restoring force per unit area, which is known as stress. So applied force F, which is applied in an area A, so stress equal to F by A. Unit of force is Newton, unit of area is meter square. So we can say that unit of stress is Newton per meter square, or it is also denoted as a Pascal. And its dimensional formula is m L inverse T raised to minus 2. Here, based on the stress and strain, 4 different conditions are given. Let us discuss all one by one. Let us go through the first diagram. As here one cylinder is given, if we apply the force and we stretch that cylinder at both the ends by the equal forces, which is at the normal to the cross section area. So this cylinder shape will restore the force per unit area, which is known as tensile stress. Now, if we apply the force to the cylinder in the opposite direction of the force, and the cylinder will compress under the applied force, then the restoring force developed in cylinder per unit area, which is known as compressive stress. Now, as we have seen that after applying the force, the shape of the object will change. So restoring force in a body, which is known as a stress. Now the effect, how that particular body will change in the dimension, that generated effect is known as strain. So here we can say that if we are applying a force, a stretching force we apply, then the length of the cylinder is going to be changed. Let us consider as a delta L. And L is its original length, as we can see in the diagram. So here the change in the dimension, it's known as strain, and here the length is going to be changed, delta L, based on the original length L. So that is known as longitudinal strain. Longitudinal strain equal to delta L by L. Change in the length divided by original length. Now, let us go through the second example, as you can see in the diagram B. Here a cylinder is available. Here we are focusing on its displacement between the opposite faces, as the length L is there, and from both the ends we are applying horizontal force at both the ends but in opposite direction. And the restoring force per unit area is developed due to this tangential force applied at both the end of the cylinder, which is known as tangential stress or shearing stress. So here, as you can see that bottom end is not displaced much, upper end will displaced by the delta X amount. So here displacement delta X, relative displacement delta X available over here, which is in opposite faces of the cylinder. So here, as the shearing stress is applied, displacement delta X is done. So this is what the dimension of physical variation, parameter variation takes place, which is known as strain. So shearing stress is developed in a body and displacement takes place. This strain is known as shearing strain. It is defined as the ratio of relative displacement delta X by its length L. So here, as we can say that theta angle has been generated. So if I say tan theta, that would be equal to delta X by L. So shearing strain is also denoted as tan theta, that would be equal to delta X by L. And this theta is known as angular displacement of the cylinder with respect to vertical reference. Now, let us focus on to the third example. A book is defined over here. Over a book, by the hand, the pushing force is applied. It is pressed by the hand in a horizontal direction, and accordingly the displacement takes place in the horizontal direction, which is very much less. So we can say that tan theta, that would be delta X by L, which is very much less and can be defined as tan theta nearly equal to theta. So here again shearing stress is developed in a body, and shearing strain, which is defined as a tan theta by the displacement delta X, which is very much less, can be noted as nearly equal to theta. Now the fourth diagram, the fourth example we are taking, the solid sphere we are taking, which is placed in a fluid under high pressure and compressed. This object will compress uniformly from all the directions. So here the force applied by the fluid, which is in a perpendicular direction at each point of the surface of a body, which is known as hydraulic compression, because this a force is generated by the fluid and the direction of the force is perpendicular to all the direction. Here, this leads to decrease in its volume without changing its geometrical shape. So here its shape is not going to be changed, just its dimension is going to reduce. So here the body will develop a restoring force internally in equal and opposite direction by applying that fluid force. And this restoring force per unit area is known as hydraulic stress, and it's that is in equal and opposite magnitude of hydraulic pressure, fluid pressure. And based on that, strain is produced by the hydraulic pressure, which is known as volume strain, and it defined as change in volume delta V by its original volume V. So volume strain is delta V by V. So here the strain is a ratio of change in dimension to the original dimension, which has no unit or no dimensional formula. Now let us go through the next topic, Hooke's law, the most important law. So here we can say that stress and strain are proportional to each other. While the stress is developed in a body, the change in size or shape will be developed, which creates the strain. So by the amount of stress, strain will develop in a body. So here the stress is directly proportional to the strain. If we remove the proportionality, can be substituted by the constant. This constant K is a proportionality constant, which is known as modulus of elasticity, which is known as Hooke's law. Hooke's law is stress proportional to the strain, which is an empirical law, and it's found in almost all the materials. Now let us go through the next topic, stress strain curve. Here the frictional or very small change in a length, which is strain, is developed, and the applied force is required to cause that strain, which is recorded. So here the stress versus strain graphical representation will be given. It gives you to understand how the material will deform as its force, continuously applied force will be increases, then how the variation onto the object is observed. So let us take first a smaller portion, OA, in a blue line. It is defined in a graph. Here if we focus OA line, it seems like a straight line. Straight line defines the linear response. Linearity given by the Hooke's law, that stress proportional to the strain. So here we can say that if smaller force is applied onto the object, then stress and strain is proportional to each other based on Hooke's law. Hooke's law is obeyed over here. And body, if the force is removed, the applied force is removed, then body regain its original dimension. So within this OA region, solid body can behave as an elastic body. Am I clear? Now, AB region, as you can see over here. Here the small curved path is shown. So we cannot say that stress and strain are proportional. Here stress and strain are not proportional to each other. So here while the body reach in that particular region, based on the stress applied, generated stress, the strain will change, which are not linear. But if that applied force is removed, then again within this region, body can generate its original dimension. So point B of the AB curve is known as yield point and point A is known as proportionality limit, because OA, where the stress and strain are proportional to each other. So A is the end point of the proportionality, which is known as proportional limit. In A and B curve, here stress and strain are not directly proportional to each other, but yet again here body can reform its original structure when the applied force is removed. So point B is known as yield point, which is a last point of elastic limit. So B point is also known as elastic limit. And at that point, whatever the stress will be defined, that is a sigma y, which is known as yield strength, as it is oriented towards the y-axis and it is denoted as a sigma y. That stress is known as yield stress. Now let us move further in the region of B to D. So here within this region, as we can see that the given force, the load is increased continuously, and based on that, stress develop in a body which exceed that yield strength. So here the strain increases very rapidly, even though small change in the stress is generated in a body. So here we can say that if the applied force is more than restoring stress is generated by a body is very much less, but its effect is larger, the dimension variation is larger. So strain generated in a body is more. So here the point C, where the load is removed, when the load is removed, so at some point C between B and D, the body does not regain its original dimension. So when the stress is 0, we can say that strain is not 0. Here B to D line is there, where if we remove the applied force, then the restoring force, the stress developed in a body would be 0. But at that point, we cannot say that strain would be 0. It means whatever the dimension variation has been done, it will not reform. It means now the material is permanently set. So here the deformation takes place within B to D curve, that is a plastic deformation. And the point D on the graph, it gives you the tensile strength, that is denoted as sigma U onto the stress y direction. So tensile strength is developed in a body at the last point D, which is the tensile limit can be there. Now beyond point D, if again the applied force is increases, then the completely fracture of the body takes place. So beyond this point, the additional strain is produced within a body. So even though the applied force is reduced, then also the fracture will occur The point E is denoted a fracture point. So here the strength and the fracture points D and E very close to each other and the material becomes brittle. So if the material is come across in that curved form, that material is known as brittle. So if this D and E points are far apart for the specific material, then this material is known as ductile. I repeat, the strength limit D and fracture point E, if these both are very near to each other, it means the material can break down, the fracture occurs onto the body very easily, and that material is known as brittle. But if D and E point are far apart, it means it requires quite more force for the fracture point. So that material is known as ductile material. Right? Here another stress strain graph is given, as you can see onto the beside. This graphical representation is available for elastic tissue of aorta, which is present in heart. So within this elastic region is very much higher, and within that region, as again we can say that material is not obeying Hooke's law. So there is no well-defined plastic region would be there, so which can be stretched to cause the larger strain. So this is what the graphical representation is available, where that tissue can be stretched and reformed by the larger force itself, which is known as elastomers. Am I clear, everybody? Here we are going to end this session. Hope you understood. Thank you.